Let's take a look at some physical properties of amines. First thing I want to talk about is the geometry. I'm going to draw this amine as though it were a chirality center. And you'll see why in a second. So this is sp3 hybridized. And as we know, our standard sp3 hybridized bond angle is 109.5. The angles here are 108. And that's because the lone pair here acts as a little more strongly than your standard carbon-carbon or carbon-nitrogen bond with its lone pair in the bond. So this lone pair pushes these three bonds a little bit further away from itself. And that makes the angle between any two of these bonds 108 degrees. And so you see that I've drawn a chiral amine here. And so it looks like amines could be chiral. This example is chiral at least. But it turns out a very interesting thing happens at room temperature. At room temperature, the nitrogen will undergo inversion, which means, essentially it means the lone pair travels through the nitrogen and comes out the other side. It is a strange phenomena, but we end up with this version of the same amine, and you can see how I've essentially inverted the stereochemistry of this nitrogen. And therefore, at room temperature, nitrogens are not chiral. It will be a racemic mixture. And we really don't spend a lot of time thinking about the fact that this amine with three different R groups is a racemic mixture. We just sort of don't worry about the fact that it has three different R groups. All right, let's look at solubility. If we have more than 5 carbons on the amine, it is not water soluble. If we have less than or equal to 5 carbons on the amine, it is water soluble. And these carbons you'd add them up from the different R groups that might be on the amine. Let's look at some boiling point properties. So propane versus ethylamine, not a huge change in molecular weight, versus ethanol. And let's look at the significant changes in boiling point. So propane boils at minus 42 degrees C. We know that it is a gas at most standard temperatures, definitely at room temperature. Ethylamine boils at 17 degrees C, so at room temperature it would also be a gas. And we know that ethanol is not a gas at room temperature. It has a boiling point of about 78 degrees C. So you can see a huge difference. Here when we install the opportunity for hydrogen bonding, we get a big increase in the boiling point. The oxygen is much better at hydrogen bonding than the nitrogen. It is a little more electronegative. It puts a greater negative charge on the O, greater partial positive charge on the H, and that allows OH bonds to hydrogen bond with a stronger attraction than an NH bond. And so we can see again a very fast increase in the boiling point, which means that the ethanol molecules are more strongly held together by hydrogen bonding than are the ethylamine molecules. Here's another series that we can compare. Propanol versus propylamine versus ethylmethylamine versus trimethylamine. So now I have different substitutions on our nitrogen, and again we see fast changes in the boiling point. So as we expected from our discussion about alcohols a few seconds ago, propanol has the highest boiling point, 97. Propylamine boils at 50, so it is a liquid at room temperature. You can see that adding one more carbon to ethylamine has a dramatic increase in the boiling point, and ethylmethylamine boils at 34 degrees. You can see that we're still maintaining the ability for hydrogen bonding to take place, but our molecule is a little more compact now that we've split off this longer carbon chain. And so we see a decrease in the boiling point. And can you guess what trimethylamine might boil at? That has a boiling point of 3 degrees, and that should be not surprising because we've essentially moved this last carbon here onto the nitrogen. Now we have 3 single carbon groups on the nitrogen. There's no opportunity for hydrogen bonding within a sample of trimethylamine because there's no NH bond, and so it has a very low boiling point of 3 degrees. Let's look at the basicity. Let's just draw a acid-base equilibria. So I'll take triethylamine, I'll react that with acetic acid, and I'll make triethylammonium cation and acetate anion. And of course we know that we can look up the pKa's of both acids and decide where the equilibrium lies. The pKa of acetic acid is 4.76. The pKa of triethylammonium is 10.76. And so we know that the equilibrium will lie to the side of the weaker acid, and that's going to be the triethylammonium. So we should have a bigger or thicker arrow pointing to the right side. So the right side is favored in this equilibrium. But you can see that any amine with a lone pair makes a pretty good base, unless we can show that that lone pair is tied up in resonance somehow. So in this case, that lone pair is free and available to act as a base. It can grab the hydrogen, making the triethylammonium. There is a table in your text that shows pKa values of different ammonium cations, which again are amines that have already claimed the hydrogen. So these are the conjugate acids of neutral amines. Remember that the higher the pKa, the better the base is on the other side of the arrow. Let's look at a few examples where resonance comes into play. So aniline is aminobenzene. And we know that that's a strongly electron donating group. We can draw some resonance. I'm not going to draw all of them, but we'll draw one at least to get an idea of how this reacts. And I think I don't need a... There we go. Okay, so now I have my first resonance structure. You can see that we've taken electron density away from the nitrogen, put it onto the ring. That makes this ring a good nucleophile. It also deactivates this lone pair as a base. So this aniline is a less strong base. Delocalization of the lone pair means that aniline is a less strong base or a weaker base. Let's look at one more example. Here's a generic amide. And the amide also can donate lone pair from the nitrogen onto the carbonyl, producing this resonance structure. That is the only other, well, that is one of the resonance structures. That's the most important for this discussion. So you can see that I'm delocalizing this lone pair into a pi bond between the C and the N. And so this is very delocalized. Amides do not make good bases at all. And in fact, they're also poor nucleophiles at this position because of the resonance stabilization or the delocalization of this lone pair.